Hi, everybody. Again, thank you so much for joining. This is, well, Happy New Year. This is our first webinar for 2022, and we are super excited to have with us Dr. Kelly Ferguson to talk about phthalates and preterm birth. Dr. Ferguson was trained at the Department of Environmental Health Sciences at the University of Michigan School of Public Health, and since 2016, she has been leading the perinatal and early life epidemiology group in the epidemiology branch at NIEHS. Her team investigates how maternal exposure to environmental chemicals impacts pregnancy and the development of the fetus and child. They also investigate oxidative stress and inflammation as biological mechanisms that may connect chemical exposures to adverse birth outcomes. So without further ado, Kelly, the floor is yours. Thank you very much for doing this.
Yeah, no, thanks for inviting me. This is so great to be able to share with people. I'm going to try sharing. And hopefully that worked okay. Everybody see everything?
Yes.
Great. Excellent. Yeah, thank you so much for inviting me to talk today. I'm really excited to be able to share some of this new research that's come out of my collaborations. And yeah, so thanks for having me. So the title of my talk is Phthalate Exposure in Preterm Birth, Findings from a Pooled Study. And I, as Marianthi said, I'm a tenure track investigator in the epidemiology branch at NIEHS. Before I get started, I just have a couple of acknowledgements and a disclaimer. First, I want to acknowledge the postdoctoral fellow I work with, Barrett Welch, who performed all of the analyses that I'm going to show you today. And I also really want to thank my analysis team for this project because they were really instrumental in providing help with planning and feedback for this study. I also have to thank all of the investigators who contributed data to the study, and I want to mention that these are unpublished findings, so nothing finalized yet. I'm going to start today by giving you a brief overview of my research group here at NIEHS, and then I'm going to go into more detail on my research investigating environmental phthalate exposure in preterm birth. This is something that I started working on when I was a PhD student at the University of Michigan. So I'm going to give you some background on previous studies, including my dissertation work. And then I'm going to share with you our new pooled study on phthalate exposure in preterm birth. I'm kind of going through the process from the cohort identification to the data harmonization and analysis. And then I'll show you the results and talk about some of our future directions for this project. The overarching research objective of my group is to improve the understanding of how the environment impacts pregnancy and childhood health. And this involves following the continuum from environmental chemical exposures to biological mechanisms, particularly oxidative stress and inflammation, to adverse pregnancy and child health outcomes. And the overall hypothesis that drives our research is that environmental chemical exposures adversely impact pregnancy and child health outcomes, and that oxidative stress and inflammation play a pivotal role in these relationships. I also have several focus areas which kind of underpin all of my research projects. So first, I seek to optimize exposure assessment by measuring repeated measures of non-persistent compounds to more robustly capture pregnancy exposures as well as specific windows of susceptibility. And I also emphasize investigation of several questions pertaining to chemical mixtures for health. I focus on mechanistic intermediates underpinning the exposure health relationships with the application of cutting-edge methods that can be used to understand mechanisms in human populations. And finally, I advance outcome assessment in all of my studies by disaggregating traditional health outcomes into phenotypes, which may have more homogeneous etiologies. And finally, a key piece of all of my research is robust validation and replication of our findings, which is something that I'm going to highlight in my talk today, where I follow up on some of our initial findings with analysis in a pooled study. I also want to take a moment to selfishly put in a plug for a hiring opportunity in my research group. So if any of the stuff that I talk about today interests you, please contact me. We're seeking a postdoctoral fellow from my group, the Perinatal and Early Life Epidemiology group here in North Carolina. We're looking for someone who has training in epidemiology, environmental health, or biostatistics with an anticipated start date of summer or fall 2022. This is a picture that I took of the campus. We have a beautiful lake and a path around it so we can take breaks to walk during lunch or whatever. I actually took this picture to show kind of the overflow of the water after a big rainstorm, but it really is a beautiful place to work. There's also positions available right now in the fertility and reproductive health group and in the breast cancer and the environment group. So there's actually kind of a lot of postdocs open at NIEHS, so feel free to contact us. Okay, back to the talk. In our study that I'm going to talk about today, we are investigating phthalate exposure in pregnancy. And phthalate exposure, as we know, is very common and it has been suggested to be associated with prematurity in some studies. So phthalate diesters are plasticizers and solvents that are used in many personal care products. They're used in vinyl plastics, like those used in flooring and shower curtains, and they're also used commonly in food and beverage packaging materials. We're easily exposed to phthalates through multiple routes, including ingestion of contaminated foods and beverages, inhalation of compounds that are off-gassed from vinyl plastic materials, and dermal absorption through use of personal care products. And once these compounds enter the body, they're quickly metabolized and excreted primarily through urine. But despite that rapid metabolism, we're exposed to phthalates so constantly that we really do experience a kind of chronic exposure. Phthalates have been associated with an array of adverse health outcomes in humans, but primarily hormone disruption and infant reproductive tract and neurologic development. As I said, I started investigating the relationship between phthalate exposure and preterm birth when I was a graduate student at the University of Michigan, working in the lab of John Meeker. We used a case control study of preterm birth from participants of the Life Codes birth cohort and measured a panel of 9 phthalate metabolites at 3 visits during pregnancy. In this case control study of 130 mothers who delivered preterm, as well as 350 controls. So we averaged the phthalate metabolite concentrations from each of those 3 study visits to create a pregnancy average of exposure, and we examined associations with preterm birth. We found that higher levels of mono-N-butyl phthalate and the summed di-2-ethyl hexyl phthalate metabolites, so the DEHP metabolites, were associated with an increased odds of preterm birth. At the time, this study really had the largest number of preterm births to address this research question, and it greatly improved on exposure assessment by creating this average of phthalate exposure during pregnancy from the 3 biomarker measurements. Since that publication, I've replicated these findings in 2 other cohorts that I work with. So in TIDES, the infant development and the environment study, we were also able to assess exposure by measuring phthalate metabolites at 3 time points during pregnancy and taking an average. And this cohort had fewer preterm births, only 57 compared to 130 in the Life Codes study, but it had a larger sample size overall. And in this study, we similarly observed associations between the MBP and DEHP metabolites in preterm birth, with effect estimates that were very similar in magnitude compared to what we saw in the Life Codes study. And we additionally observed an association with monoisobutyl phthalate in preterm birth. However, you'll note in the study that we see kind of wide confidence intervals, and which is due to the smaller sample size for the number of preterm births. We additionally observed similar results for the MBP and MIBP phthalate metabolites, though not the DEHP metabolites in the PROTECT study. The Puerto Rico Test Site for Exploring Contamination Threats, or PROTECT, is a Superfund research program study that's conducted on the island of Puerto Rico where preterm birth rates are particularly high. So we had a pretty large study population here, about 1,000 individuals total and 100 cases of preterm birth. And again, we have those averages of 3 measurements of phthalate exposure across the course of pregnancy. We conjectured that we did not see associations between the DEHP metabolites and preterm birth in this study population because exposure levels were much lower compared to what has been observed historically in the US, kind of due to the fact that exposure to these compounds has been decreasing over time. So despite the replication that I've observed in my own work, publications on phthalates in preterm from other study populations have been less consistent. So in this table, I'm showing you studies from other populations, the number preterm from those studies, the number of urinary measures in which they assessed phthalate exposure, and then the phthalate metabolites that are associated either with shorter gestation, which is the direction we hypothesize, or longer gestation. The most obvious limitation across these studies is the small number of preterm births, which is generally less than 40, with the exception of 2 recent studies from Canada and China. Another major limitation is an exposure assessment. So I talked about the previous studies I worked with where we were able to measure exposure at multiple time points during pregnancy and create subject-specific averages. But as you can see here, most of the studies that have previously looked at phthalate exposure in preterm birth have only had 1 or 2 measurements during pregnancy. And in general, as you kind of zoom out on the literature review in this manner, you might take away that they're kind of null findings. You see a number of phthalate metabolites that are associated with shorter gestation, but also a number associated with longer gestation, and the blank cells indicate that no associations were detected. So your takeaway might be that we're kind of seeing null associations with these exposures. Despite this ambiguity in the epi literature, there's actually strong biologic plausibility for a causal relationship between phthalate exposure and preterm birth. One potential pathway is through oxidative stress and inflammation in pregnancy. So in vitro studies have shown the capacity of some phthalates to cause oxidative stress and inflammation, and phthalate exposure has been associated with these biomarkers in pregnant women in human studies. Furthermore, oxidative stress and inflammation pathways are well-established precursors of preterm birth. So this is a highly plausible mechanism. An alternative pathway is through placental dysfunction. So phthalate exposure has been associated with expression of genes that are associated with trophoblast differentiation. So theoretically, phthalates could also act through this pathway to cause preterm birth. With this background in mind, we designed the pooled study of phthalate exposure in preterm birth. Our primary objective in this study was to assess the association between phthalate exposure and preterm in a large US sample, addressing the major limitation that I pointed out in number of preterm births in previous studies. Our secondary objectives were to estimate the joint effect of phthalate exposure on preterm birth, to examine exposure levels by maternal race and ethnicity and examine how those differences in exposure levels could contribute to preterm birth, and finally to investigate specific periods of susceptibility for this relationship. Next, I'm going to walk you through how we identified cohorts to include in our pooled study. I'm going to give you kind of a brief overview of how we harmonize some of the key variables, and then I'm going to describe our statistical approach. First, I'll talk about the cohort identification. So for this pooled project, we chose to focus on US-based studies in order to facilitate generalizability to the US population, and because US populations exhibit high levels of phthalate exposure as well as rates of preterm birth. In 2019, my trainee Emma Rosen performed a systematic review of all studies to identify all studies with data on urinary phthalate metabolites measured during pregnancy. So we really wanted to get all of the studies that I had published on prenatal phthalate metabolite measures rather than just the studies that had published on the association between phthalates and gestational age at delivery in order to have an unbiased sample. So Emma identified 21 unique prospective studies. Of those, we excluded 5, 4 due to a pretty small sample size, and one of the studies did not respond to an email request. And so we established data transfer agreements for those 16 studies. And I tried to play around with creating a super fun word cloud today, weighting based on the number of participants that were included for each study, and this is what I got. So it's not ideal, but you can see at least some of the studies that were included, and you might recognize some of those. Participants from these studies were recruited across 23 sites in 15 states, as well as Puerto Rico. And most of the studies recruited participants in the first half of pregnancy. And the deliveries occurred over the course of about 3 decades, beginning in 1983 and ending in 2018. We included all participants from these studies who had at least one urinary phthalate metabolite measurement in pregnancy and who had assessment of gestational age at delivery. We excluded participants who had a non-singleton delivery. There were a couple of twins in there, and we additionally excluded measurements where there was missing gestational age at the urine sample collection, where there was a missing urine dilution measurement, so specific gravity or creatinine were missing, and we excluded urine samples that were collected less than 1 week prior to delivery or after delivery. So this resulted in a final sample size of about 6,000 participants, 538 of whom delivered preterm. Next, I'll talk a little bit through the data harmonization methods. And here I have to give a big shout out to our data manager, Kate Kristenberry, who did most of this work. So in regards to exposure assessment, we examined 11 phthalate metabolites that were measured in 10 or more cohorts. And these metabolites and their abbreviations and the number of cohorts that had those measures are shown in this table. For most of these studies, phthalate metabolites were measured at the CDC, and if they were measured elsewhere, they were the protocols that were used were derived from the CDC protocols. Preterm birth was defined as delivery before 37 weeks completed gestation, and we had a mean gestational age at delivery among term births of 39.5 weeks and among preterm births of 34.8 weeks. In this figure, I'm showing you the distribution of gestational age at delivery within each cohort, and the red dashed line indicates our preterm birth cutoff. There's a couple of distributions here that might pop out to you as a little bit unusual. So the life code study, which is shown at the top, was a case control study, the only case control study that we worked with. Thus the appearance of kind of a bimodal distribution. And then the other studies that I'm showing you here in red were high risk cohorts. So in some cases, they had higher rates of preterm birth. And in our sensitivity analyses, we did examine whether removing those cohorts had an influence on our results. Here I'm showing you the covariates that we included in our final models. So cohort was included in all models as a fixed effect, and we additionally adjusted for maternal age in years, for race and ethnicity with the condensed categories shown here, education level as an indicator of socioeconomic status, and pre-pregnancy BMI. Smoking was only included in sensitivity analyses due to kind of a high proportion missing. And missing covariates were imputed for all of our analyses. For each phthalate metabolite measurement, we had a corresponding indicator of urine dilution, so either specific gravity or creatinine. And we adjusted for urine dilution by applying the covariate standardization approach, which is developed by Katie O'Brien here at NIEHS. This approach reduces bias and measurement error of the estimates. And additionally, my collaborators, Jordan Kuiper and Jesse Buckley at Johns Hopkins, showed that we can apply this method when you have measures of both specific gravity and creatinine within your sample. So this approach can allow for incorporating those measures when you don't have all of your participants with the same urine dilution measurement. Finally, for many of the participants within this pooled study, we had multiple measurements across pregnancy. So this pie chart is showing you that more than half of the participants had 2, 3, or even more measurements collected during gestation. And so we created a pregnancy average of exposure measurements for those individuals after the exposure was corrected for urine dilution. Okay, now I'll describe the statistical analyses that we performed. Our primary analysis was just a multivariable logistic regression model with adjustment for cohort as a fixed effect. And we adjusted for covariates selected a priori, including age, race and ethnicity, education, and pre-pregnancy BMI. And we were also interested in quantifying the joint effective exposure. So we applied quantile G computation, which I'll talk about more in the next slide. And we also applied G computation to examine some hypothetical interventions. For our sensitivity analyses, we examined heterogeneity by cohort by comparing the impact of adjusting for cohort as a fixed versus a random effect. We examined heterogeneity and confounding with wald tests, and we tested the robustness of our results to removal of some of those high-risk cohorts that I presented in the previous slide. And we examined the influence of some additional confounders as well. As I said, we use the quantile G computation method to estimate the joint effects of phthalates within the mixture. So we were motivated to perform a mixtures analysis to address this research question because we know that pregnant women are exposed to many phthalates simultaneously, and the joint effect of the overall mixture may be more realistic than effect estimates of single phthalate metabolites. We applied quantile G computation, which is the method developed by Alex Kyle in collaboration with the epidemiology branch here at NIEHS as an approach to estimate the joint effect of exposures without assuming any directionality of the associations and after accounting for correlations within the mixture. And the output is pretty easily interpretable, which is an advantage of the method. And it's typically interpreted as the difference in the outcome per quartile increase in all of the exposures within the mixture. Although in this analysis, we converted our estimates to the odds of preterm birth per an interquartile range increase in all of the exposures in order to compare with the estimates from single pollutant models. So now I'm going to get into the results. I'm starting off by showing you some of the exposure characteristics of our study population. Most of the phthalate metabolites that we looked at were detected in over 96% of samples, and there was substantial overlap in exposure distributions across all of the studies, as shown here for the metabolite mono N-butyl phthalate, MBP. There's a couple of exceptions. For several exposures, participants from the early pregnancy study, which is shown it's third to the bottom, the dark blue histogram is from the early pregnancy study. And so individuals from that study population had much higher levels of exposure, which could be attributable to the fact that this is the earliest study and phthalate exposure levels have been declining for most compounds across recent decades. There's also occasional instances where some studies would have higher levels of some metabolites, as with the example of the Rutgers study in this chart. So here are the results from our primary multivariate logistic regression models. These are odds ratios of preterm birth and 95% confidence intervals per an interquartile range difference in each phthalate metabolite that we examined. So we found that the phthalate metabolites MIBP, MBP, MECPP, which is one of the DEHP metabolites, and MCPP were associated with an increased odds of preterm birth in our adjusted models. The results from our sensitivity analyses indicated that our results were pretty highly robust. So effect estimates and confidence intervals were almost identical in models where we adjusted for cohort as a random effect versus a fixed effect, which suggests that there's very little heterogeneity in effects across cohorts. We also did not detect any interactions between cohort and phthalate, which would have indicated that the effect of phthalate differed by cohort. We didn't detect any significant heterogeneity and confounding or differences with additional adjustment for smoking or year of delivery. We didn't observe any differences when we removed the high-risk cohorts, although we did observe a slight attenuation of effects with the removal of the life codes participants. But this study did contribute 26% of all of the preterm births in the pooled study, so that's not altogether unsurprising. And it is important that one of the phthalate metabolites, the MIBP metabolite, the association between that compound and preterm birth did not change after adjustment or after removing life codes. Using quantile G computation, we assessed the joint effect of the 9 phthalate metabolites within the mixture that were available for most cohorts and participants. So the number of phthalate metabolites is slightly smaller here, as is the number of study participants. And we observed that an interquartile range increase in all of the phthalate metabolites within the mixture was associated with an odds ratio of about 1.3 for preterm birth, which was higher than any of the effect estimates for individual phthalate metabolites, although the confidence interval did include the null. We additionally applied traditional G computation to the same mixture in order to estimate the reduction in preterm births that we would observe for some hypothetical interventions. So for example, what would the impact on preterm birth be if we reduced exposure to all phthalates within the mixture by 50%? So this figure is showing you the estimated number of preterm births that would be prevented per 1,000 live births with various exposure interventions. Going from a 10% reduction in exposure level up to a 90% reduction in exposure level. So for the one I highlighted here, reducing exposure to the phthalate mixture by 50% would be expected to prevent roughly 11 preterm births per 1,000 live births. So this might not seem like a lot, but given that the approximate preterm birth rate in the US is about 10% or 100 per 1,000 live births, this number is actually pretty substantial. So some of the strengths of this study are that this is the largest prospective investigation of phthalate exposure in preterm birth. The pooling allowed us to obtain a large number of preterm births. We evaluated almost all of the US studies that had prenatal urinary phthalate metabolite measurements available, which reduces our risk of publication bias. And our population was diverse compared to previous US-based studies, which increases the generalizability of our findings. We had some limitations as well. So we have variation in exposure assessment across the studies, where some studies had single spot urine measurements of phthalate metabolites and others had kind of repeated measurements that we combined into those subject-specific averages. And another limitation is that some of the variables that we were interested in were not widely available across all of the studies. So an example is the presentation of preterm birth at delivery. So not all preterm births present in the same way, and those that are spontaneous in nature could be more strongly related to phthalate exposure, as we've kind of demonstrated in some of those previous studies. So we weren't able to kind of ask some of these nuanced questions within this large data set. In conclusion, despite our modest effect sizes, the health consequences on a population scale could be substantial, given that phthalate exposure is very widespread. The joint effect of the phthalate exposure was greater in magnitude than any individual exposure, although the confidence intervals did include the null, which really highlights the potential real-world impact of the exposure to this chemical mixture. So we think that additional measures to mitigate phthalate exposure could help reduce preterm birth rates among highly exposed populations. And this could include behavioral interventions, voluntary removal of phthalates from products from individual companies, or changes in regulations. An important next step for this analysis is to examine race differences in exposure levels and to investigate how those differences could potentially contribute to the observed disparities in rates of preterm birth. So there's clear evidence from the literature that phthalate exposure sources and levels differ by race and ethnicity due to historic and institutionalized racism. And in our initial analyses, we observed that non-Hispanic Black participants had the highest levels of urinary phthalate metabolites, including MIBP, which is one of those compounds that was associated with preterm birth. So here I'm just showing you that example with a box plot of MIBP exposure levels among non-Hispanic white participants and non-Hispanic Black participants from the pooled study. And you can see the clear difference in exposure levels in these two groups. So these higher exposure levels could potentially create very important differences in the attributable risks of preterm birth among Black women, which is what we plan to investigate further in the paper that we're working on now. We also plan to investigate periods of susceptibility for the relationship between phthalate exposure and preterm birth. So my previous work in the Life Codes cohort highlighted that the third trimester may be a potentially susceptible window. However, our initial results from the pooled study using generalized estimating equations show that for the phthalate metabolites that were associated with preterm birth in our models using exposure averages, the first and second trimesters may be more susceptible for the third. So these plots are showing you the odds ratios of preterm birth by trimester for these 4 phthalate metabolites that were associated with preterm birth in the overall models. So you can see that the odds ratios are elevated for the first and second trimesters, but they're close to the null for the third trimester. So this analysis becomes a bit tricky, particularly in a pooled study, when we're trying to account for the individuals who contributed data to each of these individual windows. So that's something that we're taking a closer look at now. That's all I have today. I want to give one last thank you to Barrett, who again did pretty much everything that I just showed you, and the analysis team that was crucial in developing our data harmonization and analysis plans for the paper. I'd also like to thank all of the collaborators who collected the original data and contributed it to this analysis, and who provided valuable feedback throughout the process of putting the paper together. And of course, a big thanks to the funding for this project from the Intramural Research Program at NIEHS. And with that, I'm going to stop sharing and happy to talk about our findings and answer any questions that you have. Thanks, Alex.
Thank you. Yes, we have a question. Any updates on the JAMA paper in the chat?
Oh yeah, maybe that was meant to be a direct message. So this has been submitted, and we don't have any updates right now on the submission process.
Thank you. Ruby?
Hey, super great talk. I was wondering if you had any ideas about the extent to which selection bias by selecting on live births might be impacting this relationship.
Yeah, that's something that we've thought about a little bit. Thanks, Ruby. That's a great question. One of the studies that we included in this analysis was the early pregnancy study, which was kind of focused on really trying to explore whether or not preconception, and they also measured samples in pregnancy, which are the ones that we included, but they investigated preconception phthalate exposure and how that relates to success of getting pregnant. So that is a question that has been explored in the literature, also in the Earth study. And I would say that the results are not super convincing so far in terms of a relationship between phthalate exposure and the probability of getting pregnant and staying pregnant. So I'm not very concerned about that potentially biasing our results here, but I do think it's an open question still. Tyler.
Thanks so much for a great talk. I was wondering if you could say a bit more about the potential for confounding by diet, and in particular, what sorts of dietary variables would you be interested in considering if you had access to them in these cohorts?
Yeah, that's a really good question. Something we've thought about a lot. So unfortunately, information on diet was not widely available across these cohorts. I think even in the 3 studies that I worked in where I had much more detailed information on the participants, we didn't have information on diet. So it becomes a really difficult question because we know that diet is a major source of phthalate exposure, and primarily kind of poor diets, so kind of higher fat diets and fast food consumption, those kinds of things are related to phthalate exposure. And similarly, in the reproductive literature, we know that some parameterizations of poor diet are associated with preterm birth. So it could be a potentially important confounder. The problem is that, the link between phthalate exposure and diet is not perfectly clear. And, what aspects of diet are related to phthalate exposure is kind of varying. So there have been some studies that have looked at interventions to have kind of a fresher food diet with less packaging materials. And there have been studies that have shown that, if you eat a diet that is consisting of fresher foods, you'll have lower phthalate exposure. But there is also a study in which they tried to do a clinical trial in order to provide participants with a fresher diet. And they actually saw that the participants who were in the arm that received the fresh foods and the prepared foods were, they experienced higher levels of exposure, contrary to the hypothesis. And that turned out to be because there was contamination of some herb, I think, in the food that was being prepared with phthalates. So it kind of just shows that we're really not certain about where phthalate exposure is coming from, and there's many different sources. So it's really, there's no kind of silver bullet in terms of, you know, if we were to design a study that was really trying to get at addressing this confounding issue, I'm not even really sure exactly how we would design that in order to perfectly capture the diet as a phthalate exposure source. So it's a very tricky question, and kind of remains unanswered at this point.